So why physics? I hope that tonight it will become clear why I torture you for 1 hour and a half on relativity and quantum mechanics. But the summary of what we said is like this. Classical physics is continuous and objective. You can divide space as much as you like. And it's objective, meaning this is me and this is an object. And that's it. Where's the object? I can tell you exactly where it is and the size and so on. Classical physics meaning Galileo, Newton, and so on. And of course it works. I mean, this building is standing because it works. But at some point, physicists started realizing that it was very difficult to use classical physics for something that became very important, the gases after the invention of the steam engine and so on. And a gas is a set of millions and millions of particles that move very rapidly, collide, and so on. You just can't write the Newtonian equations for all those millions of particles. And so thermodynamics came up with a different way to think about systems, and it was a statistical way. Temperature, pressure, these things are so common today. Those are actually statistical measures of movement, energy, whatever. And in doing this, they realized there was something funny going on. Energy is conserved wherever you have some kind of process, just like Newton said, but something is lost. And that's something today we call it entropy. And the easiest way to visualize it is the lump of sugar in the cup of coffee. We know exactly how much sugar there is in the cup of coffee, but we don't know anymore what the shape of the lump of sugar was. Was it a cube? Was it a pyramid? We just know how much sugar is there. That information is lost. And this property, entropy, they rapidly realized it had sort of metaphysical meaning, because they realized that it can never decrease. And so that loss of information or loss of order, whichever way you want to express it, has to increase infinitely. So there was all, I think I told you about the prospect of eternal doom. I mean, we are doomed to do this and this and that. Well, then physicists found out it's not exactly like that. But the law of entropy still holds. It's a law that doesn't have an equal sign. Okay, entropy cannot decrease, so greater or equal whenever you have some kind of process. And as I was talking, I already mentioned that today we relate entropy to order and information. So you can express the same thing as a loss of information, a loss of order, or whatever. Now, it turns out that life violates that law. Life creates order, both over millions of years in terms of evolution, of creating species that are better and better adapted to the environment, and growth. We grow and we survive in an environment that, according to the law of entropy, should destroy us. The law of entropy eventually wins because we die. But still, as long as we are alive, we are this strange kind of system that seems to violate the second law of thermodynamics, and it turns out that's actually allowed by physics because we are not a closed system. We are an open system. There's a flow of energy / matter through us, and in that circumstance, that particular case, physicists and mathematicians now know that the system can actually self-organize, which means create order, which sounds like it violates the second law of thermodynamics, but it doesn't, because there's a flow of energy. Okay? So these are systems in non-equilibrium. The classical physics hated. Classical physics like equilibrium. But when the system is not in equilibrium and there's a flow of energy, under certain circumstances, it might reorganize itself and actually create a higher level of order. And today this is usually explained in terms of complex systems, self-organizing systems. It's the same thing, just that the terminology becomes the terminology of information theory, but it says the same thing, okay? Some systems, complex systems, sometimes can reorganize themselves and create higher level of order. And one particular case of self-organization that I mentioned in passing was the oscillators. which is a different way to see things. Instead of seeing them in space, you see them in time. In time, if you have a system of oscillators, under certain circumstances, they start oscillating together. They synchronize, which is a particular case, and we'll come back today. So that was all a consequence of thermodynamics, of thinking in a different way about systems. And then, of course, electromagnetism. It's another thing that you couldn't explain with Newtonian physics, and that introduced the concept of field. You know, what's a particle, an electrically charged particle? It's a field. And as you know, then quantum mechanics decided everything can be either field or particle. So that was another way, a different way of looking at the world, not as objects, but as fields. You know. Then the relativity of quantum mechanics, a century ago, the further revolution in the way we think about the world. The relativity basically says it's all about the observer. Well, the observer had been removed from physics by Newton and Galileo. Their physics works regardless who's looking at the system. Einstein said that you cannot do that. Two things that are simultaneous for me might not be for Jim or Penny if they are moving very, very, very fast. You will get a definite speeding ticket if you are moving at that speed to see the difference. And then quantum mechanics.
I wouldn't be able to catch you. So.
Yeah, that's true. And then quantum mechanics, as you probably remember, it's even more, to some extent, even more difficult to explain in classical terms, because quantum mechanics says it's not only depends on the observer, but it's the observer that creates reality. Schrödinger's equation is a deterministic equation, but unfortunately it's about a wave. It just talks about waves. Okay, each particle is represented as a wave, and the Schrödinger's equation says how the wave evolved. Yes, but where is the electron right now? The wave doesn't tell you. The wave tells you the electron is here, 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 here. Okay, but where is it? Here, 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 here. It's only when you actually look at the electron that the electron picks one of those places, or nature picks a place for the electron. So even some scientists, not only some philosophers, speculated, well, then we create reality. If I don't look, it's just waves. I look and bang, there are objects made of particles. So that's, and then quantum mechanics introduced the concept that vacuum is not empty. The concept of entanglement, you know, sometimes two particles can get entangled, they're waves, and they will be forever, no matter how far you move them. So why is it relevant for this class? We'll see tonight, hopefully. That's because so far we've been discussing brain, mind, consciousness, using the terminology of classical physics, that we know it is either useless or false in some cases. Very small, very big, or when you have complex systems. So we actually been living in that world that, since at least a century, we know sometimes fails.